we never dropped down the low E to a low D, would we ever have Born to Run by Bruce Springsteen? You know, I think about things. Oh, by the way, I'm here to introduce chapter 25, Capacitance. Let me put my guitar away. And I'll talk a little bit about capacitance, the capacitor. I've got some tabletop demos for you folks. These headphones, I'm sure there's some capacitors in there if I take it apart. And I do have some things I've taken apart so you can see some of the components inside. Now, I say maybe. I don't know if this is not enough information or too much information. Hopefully I can strike a balance in my introductory remarks. Now, I do have a plan. What you folks learned about in chapter 23, I know I don't know if your chapter 23 matches my students' chapter 23, but Gauss's law. We're going to review how to determine the electric field for a sheet of charge. Then we're going to determine the potential, you know, as we move through the distance, the gap, you know, that spacing between the lower and upper plate. That has something to do with arriving at the equation for the capacitor. I hope you can see that. This is my cheat sheet. And then here we are in chapter 25, capacitance. So it's a three-step process to come up with the equation that gives you the capacitance of a variety of conducting surfaces or arrangements. So parallel plate, there's the isolated sphere, there's the coaxial plate sphere, you know, one sphere inside of another, separated by some distance, however that's accomplished, a dielectric. And then there's the coaxial cylinder, a cylinder inside of a cylinder, or a cylinder outside of an inner cylinder, but you get what I mean. I'm just going to focus this lesson on the parallel plate capacitor. I don't think there's enough time to derive the capacitance for all those other arrangements of conducting surfaces. So I'm just going to stick to the parallel plate, and then maybe at a later video, if the demand's there, I'll discuss those other arrangements. Anyhow, I'm going to switch glasses because this is my close-up glasses, and just give me real quick. I'm just going to go run to my table. Okay, thank you. This is a one-take video of many. All right. So I'm going to start with, I'm going to check the box. I'm going to start with reviewing electric fields. So we're going to apply Gauss's law to a thin sheet, and then bring another sheet close to it to form a capacitor. So this is how you build that concept of the capacitor. So what I'm going to show here is a edge on thin sheet. Let me give you some 3D, give you a little three-dimensional look to it. I'll put the other capacitor plate in there in the drawing, just so that, you know, stick with the plan. Okay. All right. And how a pair of plates gets charged in the first place? We can take a rabbit's fur and a balloon, and we can scrape it on the charge plate, make one negatively charged, and then through another type of induction process, we can make this other plate positively charged. But I'm going to suggest let's use a charging source. Right? I'm going to show a switch. So here's the charging source, a battery. You know, kind of like one of these, nifty. I got 3 batteries in series. Each battery is 1.5 volts. What's the total voltage? I've got my little computer here. I don't know if you can see that. Well, look at that, 4.55 volts. I hooked this up earlier to some fancy software. I gave me the potential difference across the end of its 3 battery arrangement series. anyhow, that's going to be my charging source. So when I close the switch, electrons are going to flow onto the lower plate. Okay? So the surface charge density, okay, increases. Subsequently, I don't know if I think about this, but let's say that negative charges that are flowing in this plate repels the surface electrons, forcing it back to the positive pole. How do you think about that? Rendering this plate positively charged. Well, look at that. Okay. Sorry about all that tapping. I think that drives me crazy. I watched a video of a Stanford mathematician going through this crazy analysis of the Higgs field, and I didn't understand a thing, but I did understand. I can hear the tapping of the chalk against the board. I watched the whole thing. It was quite fascinating. If you want to know about that lecture, I was fixated on something I had no idea what she was talking about. I'm inspired to actually learn what she was talking about. A challenge. Okay, sorry, I'm getting lost here, but let's keep going with this. I'm going to open the switch because I've charged the capacitor to a maximum amount of charge. So technically, the potential across these plates, once they equal the potential of the source, charges cease to flow. And at a later time, we'll talk about the rate at which these plates get charged. I might talk about it during this lecture, but we'll see. Here's the interesting thing that happens between these two plates. You earlier, when you applied Gauss's law to a plane symmetry, a sheet of charge, you got the electric field to a thin sheet of charge. If I'm not mistaken, sigma over 2 epsilon naught. Okay. The electric field between two plates, maybe it'll seem to be reasonable, but it turns out that the electric field between two plates is sigma over epsilon naught, so you get twice the electric field. Now there's a couple of things at work here that suggest as much. First of all, this lower plate will cause the surface charge density on either side to all go to the inside. Rendering this, I guess the upper surface, the charge density isn't there like it was when it was just a single lonely conducting plate. That's one reason. So the surface charge density doubles up on the lower part of the plate. So that's one way to explain it. Another way to explain this doubling of the electric field that might go from this to sigma over epsilon naught is the contribution to each other, the electric field in the vicinity of this plate, or most importantly, what's going on between the two plates. All right, I'm going to draw some vectors that represents the electric field due to the upper plate. I'm going to use red chalk, so the electric field radiates outwardly above the plate as it does, okay, below. So here's the electric field due to the upper plate. So just let me show one electric field vector. There's a bunch of them. They're all parallel. So aside from the edge effect of the electric field, inside between these plates, the electric field is uniform. Now I'm going to take a piece of blue chalk to represent the electric field due to the lower plate. So think about this. Okay, so there's the electric field due to the lower plate. You know, electric field lines radiate inward toward negative charges, and there you go. Studies show that the electric field from the other plate extends beyond the lower plate. Okay. Okay. As does the lower plate, extends beyond. positive plate. And lo and behold, what do you suppose happens above and below that parallel plate arrangement? Yeah, electric field cancels. So, and I've heard it explained one of two ways. Yeah, the electric field, uniform electric field, and because the electric field that radiates from plates, they don't diverge. So the electric field here is the same as it is out here, but then you have two opposing electric fields that cancel. That's one way to think about it. Another way to think about why you get sigma over just epsilon naught as opposed to sigma over 2 epsilon naught is you got twice the fun between the plates. You got twice the electric field. So 2 times this, you get sigma over epsilon naught. Anyhow, just to stay with what you may be asked to do in a physics problem, and that is determine the electric field between those 2 plates due to, and I'm going to start with the upper plate, or kind of fixate my attention to the upper plate. So as I check the boxes, 1, 2, 3, 23, 24, 25, let's determine the electric field using Gauss's law based on the upper plate. So I'm going to draw some people draw a rectangular enclosure. Maybe that's what I'll do. Okay, so I'm going to look at a Gaussian surface that more or less reflects, that surface such that the flux, and in this case out the bottom of the Gaussian surface, the electric field is parallel to the area vector. Okay, that seems to be the most reasonable. You can use a cylinder. There's nothing wrong with a cylinder, just as long as you got a end cap or a bottom face to help along, or jive with Gauss's law for the application of a Gaussian surface. All right. So Q enclosed. Okay. Let's specify what we got here. We got surface charge density Q over A. And maybe okay, I'll work here on this side of the board. I was going to work over here, but let's work this side. So Q enclosed is equal to epsilon naught closed integral E dot A. So the Q enclosed is going to be sigma A is equal to epsilon naught. Now the electric field comes out of the integrand because it's uniform, constant. At least that's what I think it is. That comes out of the integral, and then I forgot something there. DA. I think I heard you. You're probably, hey, dude, you're cheat sheet. You made a mistake. As you know, in most of my videos, I'm not perfect. Okay. And the integral of dA is just A. Therefore, D is equal to surface charge density over epsilon naught. Because and again, this sort of magic switcheroo, or the absence of that 2 in the denominator, is here. I'm going to go with this. You got 2 electric fields combining, so twice that. Or the surface charge density on the lower plate has doubled up because we've pulled the surface charge density above the plate, we retracted it down, so it's in greater numbers. Electrons are in greater numbers. Therefore, the surface charge density at the bottom of the plate has doubled. All right. So there's the electric field in this region of space using Gauss's law. So I'm going to check the box. Check. Now let's move right along and apply the electric potential, okay, to this scenario. I'll tell you what. Before I do that, I like to. I need you guys to. I don't want to sound all really cool and crazy, impress you with this diagram, I want to show you some tabletop demonstrations just so that you can get a feel for what this is in real life. Okay, that's what I'm all about. When I see somebody drive something, I want to know if there's a reason why we're driving that. And a lot of videos I watch, I don't know what's going on until maybe halfway through. So you're probably thinking the same thing. You have no idea what's going on, and I'm almost halfway through. So let's look at some tabletop demonstrations and also some items here that I have here displayed on this table. So as analogies go, let's first, I'm going to say here's a capacitor. See that? It's 1 farad capacitor. Here's a capacitor. It's on this this board, mostly open circuit. We haven't connected anything, but we've got a lot of components. But if you see that cylinder there, that's a 330 microfarad capacitor. I'm pointing to a pile of debris on this table, and I'll just put it in my hand and hold it out. That's that 330 farad capacitor disassembled. I tore it apart with these pair of pliers just so you can see what's inside. Drove my parents crazy. I like to take things apart. And okay, so those are the capacitors, and then there are a variety of applications capacitors, which I will get into. But I'm going to show you the simplest one, and that is storing charge. So we'll pump the charge onto the plates, and then subsequently we can discharge the plates. And I'm going to discharge the plates through this light bulb. But there's other cool applications of a capacitor. Why not? I'll go down that road. So for instance, I told you I drove my parents crazy. I like to take things apart. But here is a old, maybe 80s CD player. So this is giving itself up to science. But if you look really closely, you'll see that board, and there's lots of little cylinders in there. And those capacitors are at work, I believe, filtering, giving us a nice smooth signal. Okay, and I'll leave it at that. It's a little more complicated. Here we have a little smaller. Here's an integrated circuit. This is a force sensor. I hope the company doesn't mind that I took it apart. I probably lost the warranty if I do this. But if I look in there, I can't really tell. There's some integrated circuits, and maybe that's a diode and a resistor, and what appears to be a condenser. Okay, so I'm sure there are capacitors in this, but I can't necessarily make it out because these things are so tiny. This is a big capacitor, so I definitely can feel this, and it's singular. So as opposed to being in a device as part of the array of components that make up the logic that makes things work, I'll leave it at that. Let's go back to the simple basics. Here's the analogy I want to provide for you as I consider this battery as a pump. It's a source of electric charge. We're going to pump them onto this, push them onto the parallel plate. I have here, once again, my balloon pump, and I have a balloon. So think of the pump as the battery and the balloon as the capacitor. And the pump, okay, I got to apply force over a distance, and I'm filling this balloon. So this balloon is being filled with air, as opposed to this capacitor being filled with electric charge. Now, the capacitor has a capacity. For the most part, its capacity will depend on the pump pressure. This balloon has a capacity. It'll burst after a while. So, but nonetheless, the pressure of the balloon pump, when it equals the pressure that's inside the balloon before it pops, I'll leave it at that. I'm not going to exceed it. Now, Now that I have this balloon filled, I am going to fill the capacitor. So here's a balloon. It's full. And what do you do with balloons? You tie it off and then you got a balloon. Use it for electrostatic experiments, or birthday parties and celebrations. But I'm going to release the air in this balloon. I'm going to release the stored potential, I don't want to call it potential energy, but the air is under pressure, and after I just release it in the balloon flies away. Okay, it came down from the scene behind this video, but you saw the effects of releasing the air. Now let's charge a capacitor. Okay, not with this thing, but I'm gonna charge it with this. This is the 3 batteries that I showed you earlier, and I'm gonna hook up the capacitor to a charging source. I believe this capacitor is empty, meaning there's no charge left in it. To make sure, I'm going to hook up the terminals of the capacitor to this light bulb to see if there's any electrical energy left in it. And sure enough, the light bulb's not lighting up. Maybe I need to show you that just so that I'm not fibbing. Okay, so look at that. I've closed the circuit. I have a complete circuit, and there is no electrical energy present for the most part, or at least it's not enough electrical energy to light up that light bulb. All right, just so you know, okay, here are 3 batteries, and this might be a good demonstration in a comparative way, but I'm going to hook up this 3 batteries, 3 1.5 volt batteries in series to this light bulb, and notice the light bulb shines brightly. And if I hang here for about 3 seconds, notice that the light bulb is shining continuously at the same luminosity. All right, disconnect the charging source to the light bulb, and now let's connect the charging source to the capacitor. Now, the way I'm arranging the leads, I'm going to use the convention red on positive and the black on the negative lead. At least I hope so. Yep. And then I'm going to keep track of which lead was applied to this capacitor, because that makes all the world. Especially people that are like me, people that are worried or concerned about polarity. All right, I just hooked this up to this capacitor. Now the charge doesn't show up right away. Well, I say most, but there's a fair amount of charge that does show up right away. But I'm holding this for a period of time so that the potential across the capacitor will equal the potential across the battery. And I know I've charged this thing as much as I possibly can, given the charging source, the work that it's doing per unit charge to get it onto this capacitor. All right, again, there's a lot of details behind the capacitor in terms of the capacitance time constant, the graph. If you ever see the voltage as a function of time of a charged capacitor, you'll get an idea of what I just said earlier on having a lot of charge accumulating in the capacitor in the first 100th of a second, as opposed to over 5 seconds, let's say. All right, I'm going to remove the charging source from the capacitor. I'm going to hold the light bulb in one hand, or in the same hand as my capacitor, and I'm going to hook up my leads. And I'm not going to block the light bulb, just so you see what's going on. All right, here we go. Boom, boom, look at that. All right, now, watch the luminosity over time. Notice that it's getting dimmer. All right, is it getting dimmer? Yeah, it's just no more. So, let me ask you a question. Does a capacitor give you a continuous constant current? No. This gives you a better current, constant supply current or charge, but current flow, more continuous. So you get an idea that as the capacitor discharged, you saw the work that the charge carriers were doing on the filament. I'm not saying that the discharge of the capacitor is at the same rate as the charging of the capacitor, but you kind of get an idea. Here's the discharge of the capacitor, and here's the charging of the capacitor. And I'll talk about it in great detail later. I just don't want to run out of time. I got to check my boxes. I've checked the first box, applied Gauss's law to determine the electric field between the plates. Now we're going to apply potential. We're going to determine the potential between two plates. We're going to work per unit charge from this plate to this plate. Okay? And the reason why is that in order to arrive at the capacitance of a capacitor, we need to complete this idea. And so you will be asked to determine the capacitance of an arrangement of plates, whether it be a coaxial cylinder, two spheres that are concentric. And you need to go through this process, or you'll be asked to go through the process. You can't just like cough up the equation. I know, yeah, but take your time and embrace the challenge of determining the capacitance based on the application of Gauss's law, based on the definition of potential, integral of E dot ds, and then we'll determine the capacitance of that capacitor based on C is equal to Q over V. How do you go from Q over V to epsilon naught A over D? All right, here we go. Potential. This one's a little on the easy side. Okay. If I calculate the potential between the plates, I'm going to integrate the electric field from the lower plate to the upper plate. I'm going to go from low to high. Okay. So think about that positive charge carrier being a tennis ball on the floor. You're going to raise it through the gravitational field. We're going to raise this positive charge through the electric field. Not quite the same thing, but it's similar ideas. All right. If I look at that equation for the electric field, I don't see R there, do you? It's not an inverse proportional, whether it's 1 over R squared. It's actually a constant. So the electric field is constant between these two plates. So in terms of integrating the electric field, there's nothing to integrate. So that electric field is going to come out of the integrand. And then the distance from the lower plate to the upper plate will be the plate width. I need to draw that in there. So there's a gap. We'll call that distance D. That's the gap, the spacing between the two plates. So if we apply potential, we're going to get E, which is constant. That comes out of integrand. So we have surface charge density over epsilon naught. And then the integral ds is just s, but in this case, that distance s is d. Now, these two vectors, the distance is in line with the electric field. So we don't have to project the distance vector onto the electric field vector. They're both parallel. All right. So multiply it by d. Look at that. Didn't take long, did it? I'm going to check that box right now. Chapter 24. And I'll say something about potential and electric potential. This may be just me, but of all the topics that span electricity and magnetism, especially at this level, that's the hardest one for me to teach and explain. I am getting better at it, but I will tell you it's one of the hardest concepts. Having said that, it didn't take us very long to get there in terms of the potential between the plates. Now let's move to chapter 25. sort of the goal line. You know, here's kickoff. You know, we've moved down the field. We actually threw a bomb. And if you notice, I'm wearing some athletic gear. I'm keeping the light on for our athletic department. So we wear many hats here. One of them is teacher. One of them is coach. So if I look like a coach today, that's because after I leave this classroom, I might have to go coach. So, all right. Let's now apply Chapter 25 to all this craziness. All right, I'm gonna move over here. Can you see over here? Now, capacitance is equal to Q over V. Okay. Now, I'm going to substitute my potential equation that I just derived, having, you know, from the electric field applied potential, electric potential. Okay, and that's going to be sigma d over epsilon naught. Now, Q equals Q over A. Okay, so this is, I'm going to substitute for sigma, Q over A, Q over A times D, all over sigma. And I don't know if I did this right, but okay, it looks like the Q's go away. And then epsilon naught's going to come upstairs. The D stays downstairs. It looks like, okay, I think I was successful. So the capacitance, at least the capacitance, or the equation for a parallel plate capacitor. And now this is filled with air. This is an air gap. Okay, so I gotta qualify that. Qualify that this is an air gap capacitor. A vacuum. Okay, because if you put stuff in there, you'll change the capacitance. And I'll finish with that. So capacitance, crazy algebra, is epsilon naught A over D. Now let's go over to our cheat sheet and see if let's see if I got the same thing. Whoa, I did. So check. 3-step process. Chapter 23, 24, 25. Electric field potential. Now determine the capacitance. Okay, I'll stand back. Okay. Now I'm going to do a little racing because, as I mentioned earlier, I took apart that 330 microfarad capacitor because I like to take things apart because I want to know what's going on inside. But the interesting debris here is that we have, which comes tightly rolled up because it's cylindrical, and if you bust it apart and then unroll, what you get is actually two metal plates, and they're both plated just to insulate them. But notice the dangling paper. All right, now this paper separates the plates, insulates them. But when I opened it up the first time, there was like a slick oil in there. Now I did wash my hands afterwards. I couldn't tell you whether that oil was toxic. I'm sure California has come up with a disclaimer or a warning. You know, this could cause cancer, and I am very careful. I should be using these gloves to handle materials that I'm not very well comfortable with, but it's dried out, so maybe it's not so bad. But anyway, that paper, long story short, that paper and that oil is sandwiched, it exists between the two plates, and it actually boosts the capacitance to the capacitor. By how much? Well, I'm going to end with this equation, and where I'm going to put it. Okay, I'm going to put it here. Okay, I'm going to erase this little area here, and capacitance is equal to epsilon naught A over D. And I'll make my final gesture on the chalkboard. The stuff between these plates, not air gap, this would be if the capacitor plates had nothing in between. But if it has what is called a dielectric, and a dielectric, you know, in that electric field, with the presence of a dielectric, electric field rotates the polar, nonpolar substance that the dielectric represents, and actually weakens the electric field, which allows more charge to go onto the capacitor. So there's this thing called a dielectric constant. I think it's called kappa. But if something had a dielectric constant of 2, then that material that was inserted between those two plates has double the capacitance. Okay. I believe that's all I have for you today. So I hope that made sense. All right, I'm going to outro with, I don't know, the same thing again.